Okay, so welcome back everyone to the afternoon session today. We are very happy to have Professor Kostis Daskalakis from MIT, who will be speaking about statistical estimation from dependent data. Kostis, please.
Hi, everybody.
Daskalakis.
All right, so good afternoon, everybody. I hope you're doing well. Thanks for coming to this talk. And also, I'm sorry for not being able to be there. I'm teaching this week, and I couldn't make the trip. So I'm going to talk about statistical estimation from dependent data, and I'm going to present ideas from three different papers from the past couple of years with MIT students Yuval Dagan and Vardis Kandiros, a former MIT student Nisan Tikala, now at Google, and postdoc Ioannis Panagias, now at UC Irvine, and Shurbi Goel, who was a student at UT Austin at the time of this work and is now at MSR New York City. So let me start with reminding everybody what you know. This is the standard statistical estimation problem where we're given a set of observations, xi, yi, xi the features, yi the labels, and we assume that the labels are independent, mutually independent, and every label conditioning of the feature is drawn from a parametric distribution. So our goal is to estimate the parameter underlying how the labels were drawn, conditioning on the features, given the observations that we have. So this is very standard. And two instantiations of this model are in regression and classification problems. So here is a standard regression model. You have a bunch of features in RD and responses that are scalars. And your assumption is that for every I, label yi is sampled independently from all other labels. So, and I'm going to be using this notation, y minus I is all the labels except label I. So conditioned independently from all the other labels, yi is just some function of the feature plus noise. And noise could be from various models, let's say Gaussian. The function is from some parametric class. And our goal is to estimate the parameter of the function used in producing our examples, given the observations that we have. So this is very standard. One way to formulate a regression problem. Similarly, you can formulate a classification problem, except now the responses are binary. And now its label, its binary label, independently from the other labels, is coming from some density. For example, the probability of getting a particular label could be a sigmoid, could be proportional to x, the function applied to the feature times the sign that the label, this example takes, the label that it takes. And again, f theta could be coming from a parametric class, and our goal is to estimate theta. And of course, what we would do in such a scenario is to run maximum likelihood estimation, which corresponds to minimizing a squared loss for the regression problem as stated, minimizing the logistic loss for the classification problem that are stated. And if the models that you're using are linear models, we know that the MLE is strongly consistent, and you can get rates, estimation rates that understand our assumptions on the features and the parameters go down like root dimension over the number of samples that you have. So this is all standard. And the point of departure for this talk is from coming back to this general formulation that I have here and dropping the independence assumption that the labels are independent, mutually independent. Why would I want to drop this very standard assumption? Well, because in many scenarios of interest, the observations that you have available are not realistically independent observations, but they are collected in some spatial or temporal domain or a social network. And for this reason, they are not independent, they are dependent with each other. So dependencies show up very commonly in natural phenomena, and indeed a long line of research in statistical physics and mathematics and probability studies long-range correlations resulting from collecting data in some physical material. Dependencies also, of course, show up in social network. And again, for this reason, a lot of literature studies how peer effects influence behavior on a social network. I'm not going to dwell too much into this literature, except to say that it has been very influential, has found a lot of applications in various areas, and also has received a lot of study from various areas. Similarly, on the social network analysis front, several studies are trying to understand the effect that peer effects have, the impact of peer effects in various behaviors in networks like criminal activity, welfare participation, school achievement, participation in social programs, and so on and so forth. Several techniques have been developed in microeconomics and econometrics for modeling peer effects, and also trying to disentangle peer effects, the impact of peer effects, from the impact of individual effects when behavior is observed on a social network. And finally, closer to machine learning, there is a strand of statistical learning theory that is trying to develop techniques for learning from dependent observations. And typically, and you know, some of these works are from people in the audience. So typically, those frameworks that learn for statistical learning from dependent data use exchangeability of observations or fast mixing properties or weak dependencies among the observations, or even multiple samples. And in this work, we want to go beyond those types of assumptions and develop frameworks that can learn from observations that potentially have stronger correlations, stronger dependencies. All right, so let me jump right into this. So we want to develop a framework for modeling statistical, a model for statistical estimation from dependent data. So I will offer two models and focus on the classification model that we study in this work. And to write the sort of the proposed model, let me return to the standard regression model. So, you know, here the zebras are uncoordinated, so that refers to the standard model, the independent model. So, and this is the same slide as before, except I have emphasized that for every I, the label yi is sampled independently from the other labels. To develop a model of a regression with dependencies, I will remove this green part and explain how and propose a way in which the other labels may influence this label. So what I'm going to propose is that now for every I, yi is sampled conditioning on the other labels. And now the functional form changed, right? So I introduced this red part. So this red part is summing over every other observation some strength parameter. So the interaction between observation I and observation J some inverse temperature parameter capturing the strength of the interaction. And here I'm writing how much Yj deviates from the individual model. So what I'm thinking here is that there is a model for individual effects. So for example, xi could be, okay, so just to have a concrete example, suppose that A is the interaction matrix of all MIT students. Aij is a weight for how strong the interaction between student I is and student J is. Xi are the features of different students, and Yi are how good they are in math. And f of theta captures the individual effect based on a student's own feature, how predisposed they are to be good at math. So the red part captures how much a strong or a weak or a negative relationship may influence how good somebody is in math. So we're envisioning that the ith student is pushed to be better or worse in math, depending on the strength of the interaction of the student with other students and how much these other students are deviating from the individual effect model. And also beta star is the strength of the interaction. Maybe if beta star is 0, you go back to the original, the independent model. If beta star is not there, you get back the original model. But with that beta star in there, you have a richer model that captures a certain type of network effects. So now what is the estimation problem? You are given the network among MIT students, but you're missing the theta star and you're missing how strong the peer effect is for mathematics, for math, for being good in math. So by observing these dependent samples, you want to estimate the model, the individual effects, and also the peer effect, the strength of the peer effect. So this is one model for regression with dependent data. You can think of other models of regression with dependent data. Similarly, you can go back to the standard classification model that I was describing earlier. Yeah, is there a question?
Yeah, so this, the interpretation of this is that this is a fixed point equation for the distribution of the Ys?
Yeah, so you can, right. Yeah, that's a good question. Like, is there a distribution that satisfies this property?
Right.
So yeah, so what you can do is you can collect all the Ys to the other side and write this equation as an equation that has a matrix times the whole Y vector.
Right.
And it's going to be a Gaussian with a mean vector that is going to be the individual effects. And but the perturbation is going to be correlated. That's
so you need the norm of A to be controlled. You cannot do it with beta. Okay, the other question is, how different is this from structural equation models?
This is very closely to autoregressive models and things like this. This is not, so it's close to autoregressive models. I mean, it is an autoregressive model. It's not close to it. It is an autoregressive model. It's not an exotic model here.
So sorry, one more question. So I think I heard you say this just now, but I just wanted to confirm. So this is the same as the previous model, but where now there is a multivariate Gaussian with some off-diagonal entries?
Yeah.
Okay.
So and the way you see that is you collect, all this thing to the other side, and you write this equation in the matrix form, and you'll see that the mean vector is going to be a vector of all these f of thetas for all the xi's, and that the covariance matrix of the Gaussian is going to be, it's going to relate to beta star and the matrix and so on and so forth. And as correctly, Andrea, I think, if I could tell from his voice, said if beta star goes very large, the behaviors become so much correlated that it's hard to disentangle theta star and beta star. So this estimation problem I'm writing here is not always solvable. It's not always identifiable. It depends. Under conditions, it is. And yeah, it is very much an autoregressive model, and it's somewhat studied in the literature. Here's the, let's play the same game for the classification model. So here's the standard model. I'm going to drop the green part, make it red. Okay, and whoops. And now turn it into conditioning on y minus I. And now my sigmoid, rather than only having the individual effect, it also has the effect of the effect from my neighborhood. Now, in my example with students at MIT in math, rather than how good somebody is in math, let's make it, are they good in math or are they bad in math, right? And the probability that I am good at math has to do with my own features as mediated through this function, but also in my circle, how good people are in math. Okay? And again, I know the network, but I don't know the model theta star, I don't know the temperature parameter, and I want to estimate them from collecting information from MIT. I want to understand at MIT how strong is this peer effect, and also at MIT how individual features map to predisposition to be good at math, right? And this is today's focus. I'm going to focus on this model. And answering sort of Andrea's question, but in this model, let me put all the y's together so that it's not a mysterious conditional distribution here. So in other words, the whole vector of y's are sampled according to this measure. So it's a measure that samples a binary vector together. And this binary vector has a log density that has a sum of individual effects and also a network effect with some inverse temperature. And of course, this is just an Ising model whose inverse temperature is beta star and whose external fields are these guys. Every MIT student has their own external field that depends on their features. And also there's a inverse temperature at MIT for how strong the peer effect is. Now, again, the model contains the standard model. If you make beta star 0, you get back logistic regression, or like the standard regression model I was mentioning in the beginning. So this is quite natural, I would think, from a estimation standpoint. The challenge that one faces is that if you go to MIT and collect all this data, you basically have one sample from this Ising model. It's not like if you went back tomorrow and asked students again how good you are in math, you would get another fresh sample from that model. You have one sample and it is what it is. So you cannot resample that model. So it's one sample. And because you have only one sample, it's not clear if the ML is a consistent estimator for this. This is an exponential family. I mean, okay, if you write it in the right way, so ML would be consistent if you have a lot of samples, if you had a lot of samples, but from one sample, it's not clear if it's consistent. Moreover, it's not only that it's not clearly consistent, but also optimizing the MLE cannot be done efficiently. You cannot even do gradient steps on the MLE because you have a partition function there, and in the regimes that I will be studying, which are not going to be high temperature regimes, you cannot compute efficiently that partition function. So not only ML not necessarily consistent, but also you cannot even do gradient steps on the MLE if you wanted to. So this is the setting and the challenge. And here in this little box, I'm summarizing the settings so that you guys don't forget the notation. So like, what's the learning task? I have one sample from an Ising model. The Ising model has, so with orange, I hope you can tell the difference of the colors. With orange are things that I know. So I know people's feature vectors. I know the interaction matrix, but I don't know the inverse temperature and the theta star. So I have one sample from this Ising model with inverse temperature, beta star, and external fields, these guys. And from this one sample, I want to estimate theta and beta. I want to produce an estimate theta hat, beta hat, or theta star, beta star. I'm going to assume, I'm going to normalize the network to have infinitive norm 1. But beta star, I'm not going to restrict. So this is not going to be it's not going to be satisfying the Dobrushin's condition because beta star, I'm going to take beta star bounded, but not bounded by 1. But so this is the learning task. And the main result that we prove in the ICML paper I mentioned earlier is there is a one sample estimator. So that with probability at least 1 minus delta in the randomness of the single sample that you got from MIT, it estimates theta star and beta star in this way. So the let's say L squared error of the individual effect predictions under theta hat versus the truth, normalized, plus the distance squared of the betas is bounded by some quantity that has to do with how rich the function class is over the Frobenius norm of your network squared. Oops, I'm sorry. Okay, so what is this? So what is this log entropy? So log entropy again finds a function class that you know. This is why it's orange. X are the matrix with the feature vectors in its rows. What is this? This is the size, the best epsilon cover of the function class under the distance, which is the predictor error, the prediction error. So if I replace a function with another function, I care about my prediction error normalized. So under this distance, what is the best cover of your function class that you can get to have the error bounded by epsilon? So that, so you have this log entropy here, and you divide by the Frobenius norm. The inequality here hides exponential factors that have to do with how low temperature I am. So, again, I remind you that I have normalized my matrix to 1. So, but beta star, depending on how big it is, you go from infinite temperature when beta star equals 0, which is the independent case. If you're below 1, you're in Dobrushin's condition. If you go above 1, you're in you enter low temperature regime. So you pay exponential with how far into the low temperature regime you are. And also you pay the maximum of the external fields of your Ising model. And what I'm showing you here is a weaker form of the more general theorem that is too complex to write, that we show in the paper, which bounds these two things separately and you get better rates. If you bound them separately, you can get something better. I will make a little comment about that in a second. But so this is the result. So let's get some corollaries of this result to see how it plays out. So this is again the result. This is I have a lot of cheat sheets in my talk because when I'm in a talk, I don't remember any of the notation or anything that was said 2 slides ago. So I tend to put some cheat sheets in my slides. So This is the learning task that we're solving again. This is the main result. So let's get one corollary out of it. So suppose for starters, right, that my function class is a linear class. So suppose this is a linear model. I normalize the coefficient vector to lie on the sphere, inside the sphere. Let's kappa be the minimum singular value of the design matrix. Claim, so now the estimator also becomes polytime. There exists a polytime estimator so that the L2 norm, the L2 error in my estimation is bounded by dimension log number of samples plus log probability of error divided by the condition number and the Frobenius norm of my model. So kind of like if I put roots here and roots there, this is kind of like what you see in the independent case. So it generalizes the independent case. As long as you have some enough Frobenius norm in your network. Here's another application, sparse linear class. Sparse linear class. So you have something similar now. Let's see what happens. You pay. You have n to the 2/3. Okay, so it's not amazing, but n to the 2/3. The sparsity to 1/3. Log dimension to 1/3. Divided by the Frobenius norm. So if you take roots on both sides, it's really like you are impacted by n to the 1/3, sparsity to the 1/6, divided by the Frobenius norm. So you get something reminiscent to things you see in the independent case. Lower bound, you cannot avoid paying the Frobenius norm. So this Frobenius norm must be there. You cannot avoid it. So even in one dimension, like even if the feature vectors are one dimensional, even if you have a linear model, you cannot avoid having a 1 over Frobenius norm squared there in the denominator. That's a lower bound. That being said, okay, and here's my comment on why you might want to have a more detailed bound here rather than the one I'm showing you. That being said, you may wonder, what is this guy talking about, right? Like, why, like, you know, if I said beta star to 0, I don't care about the Frobenius norm of A. I could still estimate theta. So why am I not interpolating to the independent regime, right? So like maybe I should be able to estimate the thetas even though I'm not able to estimate the betas, right? So ultimately, right, so like Frobenius norm, intuitively, Frobenius norm should be there because if Frobenius norm goes down, of course, I cannot see beta, right? So as Frobenius norm of A goes down, I cannot really see the effect of beta. So certainly I need beta here, Frobenius norm here. But like, why can't I tell theta if this effect goes down? So that's not very clear. So one thing we can show, because here I copied everything from a previous slide, but I'm adding a new corollary. If your feature vectors are independent from a Gaussian, you can estimate theta separately, even if the Frobenius norm is anything. Right, so you get this bound, and you know, if you notice that Frobenius norm over L2 for spectral is at least 1, you get a result that doesn't depend on the Frobenius norm, right? It is not as good as the independent one, So, I'm off by a factor of D. But it's very plausible in my setting that this ratio is actually bigger than dimension, in which case you would recover the independent bound, which is root dimension over n. Yeah, so these are some corollaries of the main result. Let me stop here for any questions for the result or the corollaries, and I'll keep going. Yeah.
Oh yeah.
In the sparse case, why do you still have so much dependence on n? I mean, it's a bit of a strange formula.
You mean like this? So taking roots on both sides, you get n to the 1/3.
Yeah,
Is that what you're asking?
yeah.
Yeah. So yeah, you get n to the 1/3. I mean, we are doing we're doing something more than the independent model. So, but yeah, we're not interpolating in this case to the independent model, unless you have yeah. So so we don't interpolate to the independent case in this case. So it's suboptimal. The bound is suboptimal here. It's just we push through the covers, and that's what we got from the general result. Yeah. But the other stuff, like here, this is pretty tight. Yeah, and so here, if you have enough Frobenius norm, you recover you interpolate well to the independent regime. But yeah, this is suboptimal. It could,
Another question, what if it's not polytime? Do you know, can you get something better?
Actually, I don't know. Not that I know. Yeah, I don't know. That's a good question. Yeah, so I don't know if it's not. Yeah, it's unclear. Yeah, it's unclear. The best I know is the main result in terms of identifiability for any. Yeah, for any method. That's a good question. So two more comments, one more corollary without getting into details, and one comment, and then I will show a little bit some ideas from the proof. Okay, so in the paper we have some result for neural networks where you pay something that has to do with the complexity of the neural network class, but please see the paper for details. The other comment I want to make is, what happens if you have more than one sample from the same school? What if you have, say, many independent samples from MIT, maybe like two independent, or 5 independent, or 10 independent, or 1,000 independent? What can you do? Well, I mean, I'm going to make a silly and obvious comment that if you have L samples from your model, then you can view this as many independent. So if you have many independent samples from the Ising model, you can view as one big sample from a graph that has that has the same copy of the graph, many disconnected copies of the same graph with the same features sitting on the nodes. So in particular, you can view this as an Ising model where you have tensorized the graph and you have placed the same feature or corresponding nodes of the copies. And for this reason, you can still use the main result to see how that many samples would improve your bound. So this is the L sample variant of our result. What changes? You get a boost of L here at the cost of effectively losing log L. So, you expect to set epsilon to be 1 in n, so this is not a big deal. So really, you get a boost of L and you lose log L. And so that's what you expect to get. Oops. And that's a silly comment about multiple samples that allow you to also now interpolate in another dimension, right? So like there is, there is independence you can get as the temperature goes to infinity. In other words, beta going to 0. There is independence you get if you have many independent samples from the same high dimensional model. So you can interpolate in both directions. You can get independence from two places, and you can interpolate between existing results in two directions. Okay, so let's give some proof ideas before wrapping up. Okay, again, I'm paranoid reminding my audience of the results and the notation because I myself forget very fast. So this is the main result that I want to prove. My model is an Ising model, right? And I have one sample from it. I want to estimate in this distance. I pay something to do with some cover number by the Frobenius number. So I'm going to do a little notation change so that I don't carry f's around. So I'm going to, for every theta, I'm going to look at the vector resulting from passing all the features through that particular function. So that creates a set over n-dimensional vectors that I call H. And I can rewrite my problem as, now, this external field, which is ugly, I replace with this external field, which is less ugly. And now I have the constraint that my vector of external fields lies in the class that I define. But otherwise, the learning task is sort of equivalent. Like here, I'm looking at the trajectory of x's through the function for all possible thetas. Here, I'm just looking at all possible vectors you can create, all possible vectors from this class that I define. So same. It's like an equivalent formulation, but it clarifies a little bit the picture. Right, so in this language, really what I want to do, really, that's the problem. I want to learn the parameters of an Ising model, the H, the external fields, and the inverse temperature, given one sample from it. Of course, that's too good to happen. And the saving grace here is that the H, the external fields, which are n parameters, are restricted. They lie in some capital H class. They're not arbitrary. So rephrased in this new notation, the result is you can learn the external fields and the inverse temperature paying this amount, okay? Where now the cover, I replaced the cover that had to do with functions with the cover with just, involving this class of vectors. Same, I didn't do anything interesting. I just rewrote my problem to be a little bit prettier. Okay, so again, so now this is my learning task. This is the cheat sheet. Okay. As I was saying earlier, the likelihood of my single sample involves the partition function, which is trouble if I'm in the low temperature region. So for this reason, rather than optimizing the likelihood, which is intractable, let's try to optimize the pseudo likelihood in the hopes that the pseudo likelihood will give us a good estimate. So what's the pseudo likelihood? The pseudo likelihood is the product over nodes of my network of the conditional label of that node conditioning on the labels of the neighboring nodes. And it takes this nice form. The good thing about it, so maximizing this function over all h's in my set and all betas bounded by something, the minus log of this is a convex function with respect to the parameters. And the greatness steps are tractable, they don't involve z. So this thing is something I can actually optimize over h's and betas. But the pertinent question is it consistent? Prior work by Chatterjee, Ghoshal Mukherjee, Bhattacharya Mukherjee, and a previous paper of ours in the previous two papers that I mentioned, show that the answer is yes. So you can get good estimators if all the external fields are the same. So if they lie are they parallel to the 1, 1, 1, 1, 1 vector. And here we want to go more general. Well, here is the sketch. Okay, so we want to go more general. So here's the sketch, how you do that. So here again, my cheat sheet got increased. So I added the pseudo likelihood, and phi function, the phi function is the minus log of the pseudo likelihood, which is a convex function shown here. This is the minus log pseudo likelihood. It's a function of h vector and beta scalar. It has a unique minimum h hat beta hat. That's my estimator. The truth is not necessarily the minimum. It's somewhere here. And by Taylor, you get that the function value at a minimum, if you do Taylor around the truth, satisfies this thing, right? So this is the gradient term, this is the Hessian term, and you evaluate the Hessian at a point that's between hat and star, between the truth and the estimator. Okay, so standard things. And here's another picture, right, that shows the contours of my function. This is the minimum, this is the truth. This is the vector v connecting the truth to the estimator. This is an intermediate point h prime beta prime. And you have this holding for this, vector v hat and, all these 3 points, hat, star, and prime. Now, because hat is the minimum of my function, you get that this is smaller than this, which implies that the gradient term absolute over the Hessian term is bigger than a half. Well, that's a simple implication of the fact that this is the minimum. So far, I haven't done something super interesting. So now let's add another direction out of my truth, right? Let's call that direction U. So here is a non-trivial claim. For any direction U out of the truth, with probability 1 minus delta, for any intermediate point between the truth and the truth plus U, you have that the ratio in this direction of the gradient and the Hessian, evaluated the Hessian at this arbitrary intermediate point, that is upper bounded by some quantity that involves U, the direction that I chose, my interaction matrix, and also Y, the sample from the Ising model, the single sample that I got from the Ising model. Now, the main technical challenge in showing this result is that this phi function, right, is a function of Y. And Y is a sample from the Ising model that is in lowish temperature, so beta is not in the Brownian regime. So showing this result, that this ratio is bounded by something, involves concentration and anti-concentration of measure of functions of a Y that is not in high temperature, it's not under the Brownian. So we need such tools. We have to develop tools for showing concentration and anti-concentration of measure for functions of Ising models that are in low temperature. So in this line of work, we develop such machinery. One interesting tool from that machinery is that if you take a model that is in low temperature and you condition a bunch of variables, the conditional, if you condition on enough stuff, the conditional may get into high temperature. So the hope of doing this condition is that maybe you can prove concentration and deconcentration of some function of interest that in the low temperature regime by writing it as a sum of, by showing that components of that function resulting from fixing a lot of stuff and leaving only a few stuff fluctuating, and now these are in high temperature, concentrate or anti-concentrate. So by doing so, we can prove some interesting concentration and deconcentration results in high temperature regime and use those to bound the gradient and the Hessian of our function of the sample, y. So let's not spend too much effort parsing this slide, but let me talk about the first box. So here's an interesting result about the Ising model that we show. Suppose y is sampled from an Ising model that is in lowish temperature. It's not in Dobrushin. It's maybe above Dobrushin. Claim the linear functions at the concentrate. So the variance of a linear function is lower bounded by the norm of the coefficient vector. That's an interesting thing that we prove. We also prove some concentration of measure results under Dobrushin and use those together with the conditioning trick to get concentration results for the functions that we want in the non-Dobrushin regime. But let's not parse the result. There are some, for reference, if you're looking for a concentration of measure result, look at our paper, maybe you'll find something that is interesting for general functions of the Ising model. Just to conclude, after you show that for every u direction you get this ratio bounded, you have by epsilon covers that it holds for all directions simultaneously. And this is where this weird numerator came from. So you want to take this, that is proof for a fixed u, and say that for all u's, it holds together simultaneously. And now that you have, 4, you can put together with 2 to get that this guy, the numerator over here, is bounded by, so this, you get that, this guy is bounded by this. And because this thing then is lower bounded by half, you get that the denominator is bounded basically by some constant denominator. And from this, you can easily extract bounds on beta minus beta hat and theta minus theta hat, h minus h hat. Whoops. And this is basically what concludes the proof. All right, so hope this was kind of like gave the intuition of what we do to get this result. As I said, we prove some tighter bounds in the paper, and these are necessary to interpolate better between the independent regime and the dependent regime. And for that, you need some extra steps. You need to do some mean field approximations to get tighter bounds. That was basically it with my talk. We provide a model for classification using dependent data, an algorithm for estimating individual effects and inverse temperature. It boils down to estimating an Ising model from a single sample, a restricted Ising model from a single sample. The error is estimated in terms of the metric entropy of possible individual effect models. We need some concentration and anti-concentration results for lowish temperature Ising models. And we unify and interpolate between classical independent models and the dependent setting. I think there is a very rich space to explore, and that we only scratch the surface, really. There are a lot of other models you can consider, interesting results to prove, interesting ways to interpolate the independent case. Thank you very much.
Maybe we can have a couple of questions.
Just one comment, the anti-concentration result that you highlighted is actually, it was proved, I think, more or less by the same trick in the literature. Yeah, so
right. So we prove it using that trick. I don't know. I don't know if anybody showed it before. Yeah.
Yeah. So sorry, you doubt
It's
it was.
very easy. Yeah, it's very easy to get
Yeah.
from that trick. Yeah.
So it was proved before.
Other questions? Maybe I can ask one. So for the pseudo likelihood estimator, when H is known and for estimating the parameter beta, if you move from like high temperature to low temperature, then the rate of the pseudo likelihood estimator changes, right? On certain graphs, it like changes from the usual 1/√n rate to some 1/n to the 1/3 kind of rate potentially. So I'm wondering, is that reflected in the bounds that you have? Maybe it's true in this like mean field kind of results you highlighted.
Let's see. It's not very clear how it shows up in the bounds. Right, because we pay the metric entropy here of the H function. So it's not clear to me how it shows up.
I see. Okay.
Yeah. Yeah. But yeah.
Other questions?
I mean, I'm sorry. So I know where it shows up. I mean, it shows up here in the inequality. The inequality is hiding these factors, right, that are exponential in the upper bound you have on beta star. So you have an exponential dependency on capital B, which is a bound on beta star. That's how I know it shows up. But yeah.
I see. Okay. Yeah.
But in terms of n, I'm not sure. I don't see n playing a role here in this bound.
If there are no questions, let's thank Kostis once again.
Thank you.
Okay, so we reconvene here back maybe around 3:15. And I guess I should mention there is a reception today at the end of the session.